Hello, this is Thea Newman, the Director of Solar Avis, and welcome to this series of videos on mortality figures in Scotland during 2021. This is the second video in the three-part November update. We'll be taking a deeper dive into weeks 21 to 43. So far, we've been looking at average trends in the Scottish mortality data, focusing, of course, on excess deaths which arise from causes other than COVID. Now, in science, we can get information from average trends, but there's usually much more information hidden in the data, and that is in the form of the variations and the fluctuations about the average. And this will be the topic of today's video. Now, this is a subject which is not familiar to many people, and for that reason I've split this video into 4 parts. The first part will be very brief, just giving a quick recap on the first update video in November, just so that we're all starting from the same place. The second part will be a very brief mini tutorial on how we can measure the scale of variation about the average in data, and how we can understand the data better by smoothing those variations. And I'll talk about 2 different methods. One is looking at a running average, and the other is looking at block averages. In the third part of the video, we'll use the running average method to get a better understanding of both the excess non-COVID mortality data and the underlying causes of death data as well. This will be helpful, but we'll also see that there are some things which don't really give us immediate intuitive understanding. And that leads to the fourth and final part of the video, where I apply the block averaging method to the Scottish non-COVID mortality figures. What we'll see is that by doing that, we'll stumble across, I would say, an extraordinary result, something completely unexpected, and something at the moment I do not really have an explanation for. Before we get into this material, let me just make 2 remarks. First of all, I know from some correspondents that they have left comments underneath the videos which have not appeared or have been removed by YouTube. This, I believe, is unwarranted censorship around public discussion of these important topics. I apologize that this is the case, but it is completely out of my hands. I'm very happy to make your comments available publicly. If you send them to me by email, I will post them on my personal website. The second remark is to apologize again for the length of these videos. They always turn out longer than I would hope, but I must stress that I'm prioritizing clarity over brevity given the importance of these topics. Not everyone has the time to watch long videos. I really appreciate that, and for that reason, there are timestamps in the description below the video. So if you're in a hurry, simply click on the timestamps for the summary and you'll get the main take-home message from the video. Very briefly, this graph will be very familiar to those who have viewed the original video and also the first update. What we're looking at here are the weekly non-COVID deaths in Scotland over 2021, measured relative to the 5-year average of deaths 2015 to 2019. What we see here is that there is a steady increase through the year. And as I've explained in previous videos, what we would probably have expected is that this curve would be below 0 for the whole year, the reason being that given that such a large number of people very sadly died of COVID in 2020 and early 2021, given that they were those people were often in vulnerable groups, we would expect that a number of them would have contributed to mortality figures in 2021. Therefore, the fact that they sadly passed away from COVID earlier means that we would expect a deficit in these figures this year. Therefore, it's quite natural that we should see this curve below zero at the beginning of the year, but it's very troubling that it has been increasing through the year quite steadily. Even more so since week 21, which was late May, and for every week since 23 weeks up to the end of October, the non-COVID deaths have been in excess. That means they've been above the 5-year average for every single week. And this actually is what prompted me to make these videos, because I do find this trend a concern. What we can do is to split this curve into two parts. I'm going to concentrate exclusively in this video on the second half of the curve, in this period of excess deaths starting from late May onwards. We can see that the increase in the curve has slowed down in this period compared to the more rapid rise earlier in the year. And just a very quick summary that over that period late May to the end of October, if we add up, if I just go back, if we add up all of these excess deaths above zero, we get to a figure of 2,110 excess deaths which are non-COVID. And in the previous update video, I broke this down for you in terms of the Scottish Government categories of causes of death. Particularly troubling again was the fact that yes, that's over half of them are in this miscellaneous category of other, which indicates that there's some probably quite generic cause for this increasing trend. And the main one that I've been speaking about, although it's by no means definitive, but the main one is the possibility that we're looking at the results of the reduced medical care because of lockdown. And that's something, of course, that's just a hypothesis. I don't have any proof of that at the moment, and that's really the purpose of this study, is to try and narrow down what might be causing this trend. And to put this number into perspective, the number of COVID deaths in the same period is 1,300, and so the excess non-COVID deaths exceed the COVID deaths in a ratio of about 5 to 3. Let us now turn to this mini tutorial on understanding variation in data using methods of time averaging. So we'll just spend a couple of minutes very quickly talking about how would you go about what's called time averaging to smoothen data in a time series like the one that we're looking at, which is quite noisy. And in science we use words like fluctuations, but really that's just essentially a synonym for noise or variation and so on, the bumpiness that we see in these real-world data. So I'm going to show you two different ways we can think about it. The first is how we can take blocks of weeks and average those and get a sparser set of data points which will be smoother. And in physics, actually, we would call this coarse graining. It's like zooming out from a picture. So let's imagine then we have some data just on a weekly basis. And for example, we could say, right, we're going to make blocks in 3-week sets here. So we'll take the first 3 weeks and we're going to average those 3 data points. And then we'll take the next 3 weeks, 4 through 6, and average those, 7 through 9, 10 through 12, and we will average those 3 data points and get a new data point, and that will be block 1. These 3 will give us block 2, and so on and so forth. And so we're going to have a smoother data set with a third less points, but these will be in a smoother trajectory than the original ones. And I'm calling this register A because you can see you actually have a choice how you do this. So for example, instead of starting with week 1, we could have just ignored week 1 and we could say, well, I'm going to do 2, 3, 4 together and then 5, 6, 7 together and so on. and we could call that register B, and we would get a different set of blocked data in that case. And if I have 3-week blocks, then I have a third possibility. I could ignore the first 2 weeks and then just start with week 3 and bring 3, 4, and 5 together, those 3 weeks, and average those data points, 6, 7, 8, and so on. And I would have a third different set of these blocks. Now, if I were to ignore the first 3 weeks and start with week 4, of course, I just go back to register A again, because essentially we're just going to be creating the same series of blocks. If we were to start with 4, we would just be missing this one, but it's essentially the same averaging. So if we did 3 weeks as our sort of block that we're averaging, there are 3 different ways of choosing those, and I'm just calling them here register A, register B, and then register C. So that's one example. Alternatively, and this is something that you see more often, particularly with COVID actually, a lot of websites that have COVID data use this technique, which is quite good, called a running average. And this creates smoother data, but it actually keeps the weekly data points. So what we do here are our weeks. We take the first 3, for example, if we're doing a 3-week running average, and we'll average those and get a data point. But now we don't skip ahead to the next block of 3. We actually now choose 2, 3, and 4. And we average those and we get a data point. And then we choose 3, 4, and 5, average those and get a data point. And we'll do all the rest. And you can see we're up to 10, 11, 12 and getting a data point. And so this set of weekly data, which has been averaged, is a running average with a 3-week span, and will be a much smoother data set than this one. And these are simply different methods. I don't think one is inherently better or worse than the other. They're just different ways of thinking about smoothing the data. And you can see in this case actually this 3-week running average is really just an overlay of the 3 different registers we talked about before. So we're going to be using these 2 different methods on the Scottish excess mortality data very shortly. I wanted to show you the principle before I do them so you know exactly what's going on. And then before we do that, I just want to show you something really, really useful. So you might find uses for this in everyday life. This is a very useful rule of thumb, I'm calling it here, from statistics. Now, formally, this is a version of something called the central limit theorem. It's not universally true with fluctuating data, but it's a very good rule of thumb, and very often it gives you a very quick way to approximate what happens when you start averaging data. And the rule of thumb is that if I average a number of data points, let me say I have n data points, then the amount of fluctuation will be reduced by a factor of the square root of n. So in those examples I was just showing you, we were averaging over 3 weekly data points. So we would expect the amount of variation or noise to be decreased by a factor of about the square root of this number of data points. And the square root of 3 is roughly 1.7. Alternatively, if I took a wider set of weeks as my block or as my running average, say 5, then we would reduce the variation by more. But you see, this is quite a mean rule of thumb. It says that you get sort of diminishing returns. So even though we've gone from 3 to 5, our reduction is not that impressive because the square root of 5 is about 2.2. So by almost doubling the size of the number of points that we're averaging, we don't get very much improvement on the reduction. And this is actually something you see in statistics. It's quite hard to beat down the noise, and it's because of this rule of thumb. So if you wanted to, say, reduce the noise by a factor of 10, you would actually need to use 100 data points to average to get that variation down by a factor of 10. So this is a very good rule of thumb to use, and we'll be using that to highlight some very unusual features of the data that is worth you sticking around for later on in this presentation. I hope you found that interesting and useful. Let us now apply the running average method to the Scottish mortality data and see what we'll find. Right, so let's start by looking at some running averages. And here again, I've got the data. This is weeks 20 through to 43. And it's our famous old curve. We're looking at the non-COVID deaths relative to the 5-year average. It's always positive in this period, so these are always excess non-COVID deaths each week. And I've fitted a straight line through those points, but that's not necessarily terribly informative. It is saying that there's an increasing trend. Let's see if we can do a little bit better. So the first thing I've done here, I've put two very faint lines, and these are what are called standard deviations. I won't go into the technical details of that, but this is really just a very simple measure to tell you how big are the variations. And you see this band gives you a pretty good sense of how much the data varies about this straight line. And we're going to compare now. If we do 3-week running averages or 5-week running averages, we can see how much of a reduction in the variation do we get. So let me just make those points smaller so we don't get too confused looking at the graph. And I'm now going to plot on here the 3-week running average. So what we're doing for each point on this graph, for example, this point here is an average of the one at the same week and the one before and the one after. And then this point would be the average of this week and the one before and the one after, and so on. So we're doing this 3-week running average, and you see we do get a slightly smoother curve. It's still quite highly varying, I would say. And what we can do is actually do a little bit better and do a 5-week running average. And what we see is actually by just going to 5 weeks instead of 3, we get a lot of reduction. Let me show you those two curves. Here's the 3-week running average, quite a lot of variation. We go to 5 weeks, this becomes a very smooth curve. And that actually goes against our intuition from the rule of thumb that I was talking about. So that tells us maybe there's something a little bit unusual about this data. We can measure the standard deviation of this running average curve, and what we find is actually that it's quite tight here, tightly constrained about the best line fit, and the variation is actually suppressed by about a factor of 5 if you compare this best line fit to the 5-week running average variation compared to the original data. It's about a factor of 5. Whereas again, naively, we would expect a factor of about 2 if these were sort of typical fluctuations. So already we're sort of getting an insight that there's something a bit unusual maybe about this data. We got a very high degree of suppression of the fluctuations just by doing a 5-week running average. And one thing we see very clearly from this running average curve is, yes, that data is really increasing very smoothly. So there's certainly an increasing trend in this period. Now what we can also do is go to the individual causes of death. Remember, there are 5 categories that the Scottish Government places non-COVID deaths into. They're cancer, dementia, Alzheimer's, heart disease and stroke, lung diseases, and then this category other, which would be a miscellany of other diseases, but also things like accidents and suicides, homicides, and so on and so forth. And for the 23-week period, weeks 21 to 43, I'm showing you the data for each of these causes of death. And the sum of all 5 of these is the thing we've been looking at before, the total non-COVID excess mortality. So these curves are relative to the 5-year average for each cause of death. And all I've done in these plots is fit a straight line to them. And what you see really is that if we rank the gradient or the slope of these straight lines from smallest to largest, we see that cancer has a very, very flat line here, which kind of tells us that it's not really increasing over the period. It's really just wiggling around some average value, which is positive. So there are excess deaths in cancer, but they're not increasing week by week in this period. On the other hand, if you look at the category other, this is concerning for two reasons. First of all, it has the largest gradient, so it is increasing each week. I think more importantly is that it's well above zero. So for all of the 23 weeks, this other category is quite strongly positive. It's not even close to zero. So there are significant numbers of excess deaths in the other category, and they are increasing faster than any other cause of death, according to this straight line fit. And then the other three are, I would say, relatively similar. You can see here from the slopes. Now what we can do is a 5-week running average for all of these causes of death, and so there they are. And this pretty much mirrors what we've just been saying. I would say the 5-week running average for cancer is kind of wiggling all over the place. It tells us that there's not really any sustained trend there. For the other category, the 5-week running average is smoothly increasing on the whole. And the other three, I would say, are somewhere in between. Perhaps with respiratory, we remarked in the last update video that this actually is relatively strongly negative. And that's because we would think that many of the COVID deaths would have been in patients with lung disease, and therefore non-COVID deaths from respiratory illness would be suppressed in this period, and that's what we see here. But it is returning back to the baseline and sort of plateauing there. So the respiratory sort of looks like a plateauing at the baseline, whereas the dementia Alzheimer's and the circulatory, I would say, are increasing pretty smoothly above the baseline. And again, this category other is probably the most concerning of all in these causes of death data. So let me just help you by plotting all of those 5-week running averages for the different causes of death on the same graph. That will be interesting because we'll get an idea of the scale, because the y-axes are different in all of these 5 graphs, but if we plot them on the same graph, you'll see here that category other has significantly the most excess deaths, and then the next comes circulatory, which is probably 50% lower in terms of the scale of excess death in that category. Then we have dementia and Alzheimer's, which is lower again, and then we have respiratory. And it's really very striking, there's no reason at all why this has to be the case, that these 4 curves essentially do not overlap with each other, which is kind of odd. So there's like a hierarchy built in to the excess deaths for each cause of death. They're all increasing at, let's say, roughly similar rates, although the other category is increasing a bit faster, but they're sort of in a hierarchy where they don't essentially overlap. One doesn't overtake the other over this whole period. That's a bit odd. And then let me plot the cancer curve, and what you'll see there is that it just kind of wanders through all the rest of the data. So cancer's not playing this game of the hierarchy, it's just doing its own thing and essentially not really increasing over the period, but at a sustained positive level of excess death. Adding all of these together gives us the total non-COVID excess deaths over the period, which is the curve that we first looked at with the 5-week running average. And you see that here quite strongly and smoothly increasing. So these relatively small gradients of these different causes of death compound when you add them together to get a interestingly compound to give you a higher gradient here in the total non-COVID excess death. So just to summarize this here then, so the category with the fastest increasing excess deaths is the category other, And as we saw earlier on in the talk, that's also the category that has by far the largest number of excess deaths. It accounts for over half of the excess deaths over this period, non-COVID excess deaths. And the slowest is cancer, which I think is roughly constant over this period, although giving a significant contribution to excess death. And then interestingly, the 5-week running or rolling average for the total, as we remarked, is showing a significantly higher level of suppression of the fluctuations than we would expect by that rule of thumb. And what's quite curious is that that effect is not visible in the individual causes of death, which is a bit odd, because you might think that, well, those fluctuations are being beaten down, the noise is being beaten down in the 5-week running average, because that's happening in each of the individual causes of death, but it's really not the case at all. So when we look at the 5-week running averages for the different causes of death, we see that the suppression of the variation is really quite what you'd expect from our rule of thumb, just a bit bigger than 2. Another way of thinking about that is, what number of weeks would you have to average to get the degree of suppression that you measure? And it's a number between 4 and 8, which is, we're sort of in the ballpark of 5. So there's nothing surprising going on with the suppression of variation in any of the causes of death. However, there's some, interestingly, shows a very significant effect, and that's a curiosity, and we're going to get an insight into that in the next and final section of this presentation. Something again that's worth hanging on for, because I think it is quite a remarkable finding and it must have an explanation, although I do not know at the moment what it is. And now in the final part of the video, we'll try to get some more insight by using that blocking averaging method, and get ready for a very interesting discovery. So let's take another look at this smoothing, but this time we're going to be using 3-week blocks instead of a running average. So here's my raw data, and as before, I'm just showing you the standard deviation, so you have an idea of the scale of the variation in that raw data. And I'm going to make those points smaller, and let's start with a particular register for these 3-week blocks. I'm calling that register A, and you can see, for example, this point here is the average of these 3, this point is the average of these 3, and so on. So register A is basically starting with week 21 through 23, and then 24 through 26, and so on. And if we look at this curve, it seems to have quite a lot of variation. We can measure that variation, and the scale of it is about what we would expect. It's about, we've had a suppression of the variation by roughly a factor of 2, which is what you would expect if you have 3-week blocks. So that all looks very reasonable. Let's now shift the register by 1 to the right, and we'll call that register B now. Here it is. So this point here, for example, is the average of these 3, this point is the average of these 3, and so on. And we have a very, very similar plot. We see quite a lot of variation there. We can measure that standard deviation, and it's very similar to register A. And so again, fluctuations are as expected. Now, I wouldn't be talking about this if register C was going to be the same. So let's see what happens to register C. Here's our data, and now we're just going to be shifting one more time and averaging blocks of 3, and this is what we find. It is extraordinary. When I first saw this graph, I almost fell off my chair, because what happened to all the variation? It doesn't look like data anymore. It looks like some computer simulation. So this point is the average of these 3, this point is the average of these 3, this point is the average of these 3, and so on. And we can measure the variation here, and it is absolutely tiny. In fact, it's almost a factor of 7, whereas we're expecting from our rule of thumb a factor of 1.7. So let me just summarize that for you. Of the 3 possible registers, when we have 3-week blocks, one of them essentially completely suppresses the variations in the data. The first 2 registers that we looked at, they had a suppression of variation roughly a factor of 2, and as I explained, we can sort of reverse that into how many weeks would you need to average to get that degree of suppression, and it's around 3. So that's all completely consistent with doing this 3-week blocking. But look at register C. The suppression of the variation is almost a factor of 7, and when you reverse that and ask how many weeks would you have to average to get such a large degree of suppression, it's 43. But we're only averaging 3. So this is very, very, very hard to understand. But we see now why that 5-week rolling average had a very heavy suppression of variation, because remember, those rolling averages are sort of overlays of essentially block averaging. And so we have certain registers in the raw data that essentially have no variation. And that's what's going to cause in the rolling averages or the running averages a much bigger suppression than we would expect. So this is perplexing, particularly when we remember that this curve for the non-COVID excess deaths is actually comprised of 5 separate curves, and let's look at those. Remember, we have 5 non-COVID causes of death, and it's the sum of those data sets that gives us the total that we've just been looking at. So what I'm plotting here in register C, the one where the total non-COVID deaths have this remarkable suppression of fluctuations, I'm plotting the 5 different categories of causes of death. Now what I expected to find was that perhaps 2 or 3 of them would show a similar thing, that in this particular register, when I did a 3-week block average, that I would just get essentially a straight line, and that would help me understand then how by adding these I also get essentially a straight line of data. But actually that's not the case. Remarkably, for all 5 causes of death in this register, the curves are happily just bouncing around. There's very healthy, if you excuse the term, a healthy degree of variation in those curves. And yet the sum of all 5 of them has no variation. Let's just put some numbers on that. So just to summarize what I've just said, the almost completely suppressed variation in this register of the non-COVID deaths is not reflected in any of the underlying categories of causes of death. Here we have those 5 categories. Here's the amount of suppression of variation, and it's all roughly around a factor of 2, which is what you would expect when you're doing this 3-week blocking. And if I sort of back out the effective number of weeks for all bar one of these, again it's roughly around 3. It's just circulatory is a little bit higher, but it's nothing compared to the total, which has this extraordinarily high degree of suppression of fluctuation. So the only way to understand this is actually that the deaths that are occurring in these different categories, when registered in this register, are not independent of one another. They must be anti-correlated. Sort of one of them has a sort of a peak over a particular period, another must have a dip, so that when you add them together you get this perfectly straight line. And of course this really has one scratching one's head. I was explaining to a friend of mine, this is a bit like asking 5 composers in 5 different rooms to write a few bars of music, and they can write basically any music they like. Maybe you just say to them, but it has to be 4 measures, and it can be for any instrument, and then you bring them together. Now what you would expect is that when you played those 5 pieces of music together, you would have literally a cacophony. namely a lot of dissonance and variation. But imagine if you did that and instead you heard a beautiful harmonized sort of Baroque sound. You would be very, very perplexed, and your only conclusion could be either it was an extraordinary fluke or there had been some degree of communication between the different composers. So just to summarize now, this is really the surprising result that I've been sort of advertising through this, again, rather long presentation. I do apologize for the length of these, but I really endeavor to be clear, so I'd rather clarity than brevity, given this is such an important topic. Here is a plot of the data with 3-week block averaging in this particular register. And remember, these data points come from the sum of excess mortality in 5 different causes of deaths, and over a 23-week period they lie along an almost perfectly straight line. The existence of this curve is a mystery to me. You can actually estimate, given that we know what degree of fluctuation we would be expecting, you can estimate what's the chance just randomly that 8 points would actually lie along a very, very straight line. And crudely, you would expect this to occur 1 in 10,000 times. So I don't think we can seriously regard this as having arisen from just a fluke. There's something underlying this, but it's a mystery to me. It's telling us something, I think, about both what's going on in terms of mortality and different causes of death, and it's probably also, of course, related to the manner in which mortality data is codified in Scotland. And there may be certain sort of resonances of timescales with the way in which deaths are registered, perhaps, and particularly for different causes of death. I'm not a doctor, I don't work in the government, I don't know the sort of administrative mechanics of how all of this data is collected, but clearly this register C, this choice of blocking the data in this particular set of 3-week blocks, is somehow resonating with some administrative sort of mechanics. I think that must somehow be the case, I believe, given that the other 2 registers are absolutely normal in terms of the amount of variation that they show. So it will be very interesting to see in a week's time when we have the third of the next set of 3 weeks. We actually have 2 weeks of data, but we'll have the third of that next set of 3 if the 9th point lies on this line. It would be remarkable if it does. But I think if real world data somehow, miraculously arranges itself in such a deterministic, non-varying fashion, we should at least use it with caution to make predictions. And so what we'll be able to do is use this curve to make some kind of estimates for the future amounts of non-COVID excess mortality that we might expect in the months to come. And that will be the topic of a much shorter and final update video as part of this November series. Well, as I used to tell my daughters, in science, never be surprised to be surprised. That's really the whole point of research and analysis, is to figure out how things work, and things are often different to what our naive expectations might be. So I'll keep scratching my head trying to understand how on earth all of the variation disappeared from the data with that form of block averaging. It's certainly quite an intriguing result. At the same time, though, I do think it might be quite useful because it gives us a degree of confidence to use that method to make fairly sharp predictions for the weeks and months ahead. And that will be the subject for the third and final update video in November, hopefully one that's quite a bit shorter than the first 2 have been. So with that, let me thank you again for your interest and for your time, your very, very precious time in watching these videos. If you do think that they are useful, please do pass them on to others, because I really want as many people as possible to benefit from a better understanding of what's going on around them and using the data that the government is so freely offering us to analyse if we so wish. So with that, thank you again, and I will see you next time.